one of the Sentinel Earth-observing satellites. They occupy low Earth orbits that take them over the poles. In similar orbits, the swarm satellites monitor changes in the Earth's magnetic field. In a much higher orbit, the GOES weather satellite hovers above the United States. It orbits at the same rate that the Earth revolves. The New Horizons probe does not orbit anything. It was launched on a flyby mission past Pluto, and it continues into the Kuiper Belt. Satellites are expensive. Designed to operate at extreme temperatures in the vacuum of space, they cannot be maintained. They must perform faultlessly for years. Yet every satellite depends on the brute force and precision of a launcher to deliver it to an exact orbit.
Stop.
Launchers are expensive too. They have varying capabilities and varying reliability, but new developments in rocket technology are changing what can be achieved and how much it will cost. The days of giant state-owned corporations launching their own satellites are over. Rocket builders sell their services to commercial or government clients. In October 2014, an Antares rocket built by Orbital Sciences was set to ferry supplies to the International Space Station. The launchers are generally reliable, but space is difficult. There is still a 7% failure rate. This fundamental step of leaving the Earth's surface relies on a small group of international companies that build heavy-lift rockets. The most iconic booster in operation today is the Russian Soyuz. It's not the biggest or most powerful launcher, but its history stretches back to the earliest days of space exploration. Variants of the Soyuz launcher have been in continuous production since 1957, and they have made more than 1,800 trips to orbit. Since the demise of the space shuttle, the Soyuz remains the only human-rated launcher in operation, and both ESA and NASA rely on it to ferry people to and from the International Space Station. It is a direct descendant of the Vostok launcher that sent the first man into space. On the 12th of April 1961, Yuri Gagarin rose to orbit on Vostok 1, designed by Sergei Korolev. The design, featuring a central core surrounded by 4 strap-on boosters, was originally conceived as the first nuclear missile. But as Soviet warheads became lighter, the launcher was adapted for manned trips to low Earth orbit. Today, 4 variants of the Soyuz launcher are in operation, and they launch from 4 different sites. Many of the simple design features in the Soyuz have contributed to its reliability and low cost. It was estimated that Russia could launch 20 expendable Soyuz carriers for the cost of 1 space shuttle launch. Though the basic layout of the Soyuz is still recognizable after 60 years, it has evolved. The design has seen several generations of engine upgrade, with the guidance system continually being refined. Final assembly at the launch site sees the 4 distinctive boosters flanking the central core attached first. In Russian, they're known as carrots. Each booster and the core have one rocket motor discharging through 4 main fixed chambers. For guidance, the boosters have 2 additional small swiveling nozzles on their outer edges, while the core has 4 guidance nozzles. With the boosters and central core united, the assembly is now lifted onto its specially adapted railway truck. At this stage, it weighs just over 20 tons. When it's fueled, it will be more than 250 tons. The 4 boosters are known as the first stage. Even though they ignite at the same time as the central core, that's known as the second stage. Then, if the assembly is taking place in Russia or Kazakhstan, the third stage and the payload are fitted. This is the gamma-ray astronomy satellite Mikhailo Lomonosov, being prepared for the first launch from Russia's new cosmodrome at Vostochny in Siberia. The launcher and satellite are all assembled horizontally, a technique that is straightforward and practical. At Baikonur, the original Soviet launch site still leased by Russia from Kazakhstan, rollout usually happens at dawn. Baikonur is the only launch site where the Soyuz can carry a human payload. All of the Soviet Union's history-making flights started from the Baikonur Cosmodrome. The area's sparse population was one of the main reasons the Kazakhstan location was chosen. The rocket is delicately moved towards the firing ring, where it will be held in place by the 4 tulip petal arms. It takes about 1 hour to bring the launch vehicle to the vertical. As the lifting arm withdraws, the 4 support arms are joined by fuel and electrical umbilicals and 2 halves of the service gantry. Ground staff will have access to every part of the launcher, and the cosmonauts will enter their spacecraft via this gantry. Technicians will spend the next 2 days checking the rocket and preparing it for launch. When fully loaded with fuel, its weight will increase by a factor of 15 to 305 metric tons. Soyuz carrier rockets also launch from the European spaceport at Kourou in Guyana, and from here the rocket is erected without its payload. Because of the equatorial location, the Earth's spin makes it easier to reach orbit. A Soyuz launched from Kourou can lift considerably heavier payloads to orbit than it could from a Russian launch site. However, Kourou's tropical location has 10 times the annual rainfall of Baikonur, and a mobile gantry that protects the rocket is necessary. Like the other European launchers, the satellite is attached to the Soyuz while it is vertical. 5 hours prior to launch, the fuel is gradually introduced. The liquid oxygen boils at minus 182 degrees C, and it is constantly replenished. At 36 seconds, the first umbilical mast retracts, leaving the rocket on internal power. Soon after, the fuel connection swivels away, and the turbo pumps begin feeding fuel and oxygen to the engines. The engines are closely monitored as they are gradually brought up to full thrust.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, top, décollage, lift off.
A guidance computer in the third stage maintains the launcher's attitude via the vernier nozzles around the first and second stage chambers. Near the 2-minute mark, the boosters shut down and are jettisoned. At 85 kilometers, the payload fairing splits and falls away. 5 minutes after liftoff, and at a height of 169 kilometers, the third stage takes over to accelerate the satellite and its upper stage to escape velocity. Less than 10 minutes after launch, the upper stage guides the satellite to its designated orbit, while the rest of the launcher falls back to Earth. The American Delta IV Heavy is designed to orbit massive payloads or to hurl probes out of Earth orbit at incredible speeds. When it first flew in 2004, it had the greatest lifting capability available. The first and second stages, as well as the 2 boosters, are all powered by cryogenic hydrogen and oxygen. It can lift more than 28 metric tons to low Earth orbit. The Delta IV Heavy is made by the United Launch Alliance, a collaboration between Lockheed Martin and Boeing. It was designed to meet US military requirements. It has launched 2 NASA missions, but its other 8 launches have been classified reconnaissance satellites. Services have not been sold to commercial clients. Recently, a Delta IV Heavy was prepared for perhaps its most significant launch. It was mated with the Parker solar probe and its STAR upper stage. The Parker probe will be the first satellite to fly into the Sun's corona. And though its launch weight of just 685 kilos may seem puny for such a large launcher, Parker must leave the Earth's orbit at near record speed. After a brief period in a parking orbit, the second stage reignited to break the bonds of Earth's gravity. The final kick, delivered by the solid-fueled upper stage, gave the Parker probe the second fastest departure from Earth, and with the help of the Sun's gravity, it will reach 668,000 kilometers per hour, making it the fastest man-made object ever. In 2001, SpaceX founder Elon Musk hatched a scheme to establish a greenhouse on Mars and began trying to buy a Russian launch system. The space industry laughed, but they're not laughing now. Because he couldn't buy a rocket, he built his own. Musk knew American launches were too expensive, and a little research convinced him he could undercut the established aerospace giants. In design and manufacture, SpaceX focused on simplicity and reliability, with a view to keeping costs down.
Of the Falcon 9 rocket and the Dragon spacecraft, packing science and supplies for the International Space Station, humanity's home in low Earth orbit.
In 2012, SpaceX flew the first commercial resupply mission to the International Space Station. SpaceX designed its own spacecraft, the Dragon, to carry out these resupply missions.
Let's use some contact with a test 1.
To date, SpaceX has completed 11 successful supply trips to the ISS, with 7 more booked. Unlike all the other cargo ships that visit the space station, the Dragon is capable of returning to Earth. The Falcon 9, the company's workhorse, was criticized because it has 9 separate rocket motors. Old rocket engineers argued that there were too many moving parts with a higher risk of failure. The Merlin engine, developed for the original Falcon 1, continues to be refined, giving the Falcon 9 a steadily improving lift capacity.
Past the speed of sound, it's now subsonic.
Soon it became clear what the multiple engines could achieve. Without its fuel load, the spent first stage falling back through the atmosphere was very light, and just one engine could enable a soft landing. If this worked, it meant reusable stages would drastically cut the cost of launches. A pinpoint landing on a remotely controlled barge required so many new techniques, and space experts were skeptical. A landing leg had collapsed and was redesigned. Soon, these return trips were routine. Though landing capability reduced the maximum payload by 30%, it also drastically reduced launch fees. Next came the Falcon Heavy, essentially 3 Falcon 9s strapped together. In 16 years, SpaceX had gone from laughingstock to builder of the world's most powerful launch vehicle. This first flight was to be a pure demonstration. Its dummy payload was Elon Musk's red Tesla Roadster. The car would go into orbit around the Sun. The plan called for the 2 boosters to land back at Cape Canaveral. The central core would return to a barge at sea. Potential customers were watching the demonstration closely, and crowds who gather along the Florida coast to see a launch now wait to watch boosters returning. The car, rigged with cameras, went into a solar orbit, but in the mission's one failure, the central core missed its barge. The US Air Force will be the Falcon Heavy's first paying customer. The entry into the launch market of a company aggressively trying to reduce the cost of access to space is changing the space business. Today, SpaceX remains the only launch provider that openly publishes the cost of its services. The Ariane 5 is the European Space Agency's heavy lift rocket. It features a liquid oxygen, liquid hydrogen first stage, flanked by 2 solid fuel boosters. Though the Ariane 5 is not the most powerful launcher, it holds the record for heaviest payload to geosynchronous transfer orbit. The equatorial launch site in Guyana makes orbits of low inclination easier to achieve and is an attractive feature for paying clients. The Ariane 5 ECA is the 5th and final version of the 5 series, which will soon be replaced by the Ariane 6. A new version of the Vulcain rocket engine is being developed for Ariane 6, which will be cheaper to build and to launch. New facilities are being constructed for the Ariane 6 at the Kourou spaceport, including a new vehicle assembly building which will see a change from vertical to horizontal integration. But the Ariane 5 still has much to do. 18 launches are scheduled before its replacement begins flight testing. The stages are fabricated in Europe and cross the Atlantic by ship. At the launch site, the central stage is raised to the vertical. Slightly more than 30 meters long, the core stage is essentially a fuel tank divided into 2 compartments with a rocket engine at its base. Each solid fuel booster arrives on its table in an upright position and preloaded with propellant. The upper stage, that will on this mission deliver 4 Galileo navigation satellites to their target orbits, is fitted. The satellites, clustered about a central dispenser, are then attached to the upper stage before the fairing that protects them during the trip up through the atmosphere is lowered into place. The Ariane, on top of the launch platform, begins its journey at a snail's pace. The Ariane 5 is operated by Arianespace, who have launched more than half the commercial satellites in operation today. Russia's heavy-lift Proton launcher started its life in 1965. It was originally designed to carry a 100-megaton thermonuclear weapon to targets in the US. It was never deployed as a missile, instead evolving into a successful heavy launcher. It delivered several modules to the International Space Station, and one of its recent high-profile successes was the launch of the first ExoMars probe. But the Proton has not been without its problems. Developed during the Soviet era, its manufacturer Khrunichev was reliant on the Ukraine for key components. And when launched from Baikonur, the Kazakh government was not keen on the extremely toxic hypergolic fuel it used. There are claims that acid rain falls after some launches, and that parts of Russia and Kazakhstan are being poisoned by the unsymmetrical dimethyl hydrazine that powers the Proton. At Baikonur in July 2013, a Proton-M was set to launch 3 Russian GLONASS navigation satellites. An investigation found that the rate gyro package had been installed upside down. It was not the only recent Proton failure, and questions about quality control were being asked. Though the Proton still has launch commitments for several years, it will be phased out. Startup company Spacelab is poised for its first commercial launch. Their rocket, called the Electron, can deliver light satellites to low Earth orbit at prices that completely undercut the rest of the market. The launcher makes extensive use of carbon fiber in the construction of the tanks, and Spacelab has developed an engine with a radically new fuel cycle. Named after physicist Ernest Rutherford, the engine is largely constructed with 3D printing techniques. The liquid oxygen RP-1 fueled unit uses brushless electric motors to operate its turbo pumps instead of pre-burning fuel for the same purpose. The batteries powering the process add weight, but they save on fuel and give engineers finer control when throttling the engine. The launch site on New Zealand's North Island Mahia Peninsula is perfect for the busy schedule that Rocket Lab envisions. With the advent of microsatellites, smaller carriers like the Electron are becoming an attractive launcher for a new area of the launch market. Arguably, the most significant scientific instrument in history has been the Hubble Space Telescope. It has changed our understanding of the universe, yet it has posed serious new questions about the nature of matter itself. Hubble has confirmed the widespread distribution of black holes and has viewed light from galaxies more distant than anything previously seen. As well as its scientific discoveries are the stunning images. In 1609, Galileo built an early telescope and soon turned it to the night sky. The telescope was a powerful tool that led to a complete re-evaluation of the Earth's place in the universe. In 1668, Newton invented the reflecting telescope to eliminate the problem of uneven refraction of the different wavelengths of light. The reflecting telescope became the design of choice for astronomers, and in 1781, William Herschel used an instrument he had built himself to discover the planet Uranus. The Newtonian telescope was scaled up to immense proportions, and in 1924, it was with the 2.5-meter Hooker telescope at the Mount Wilson Observatory that Edwin Hubble realized the Milky Way was not the universe, but just one of countless galaxies. But there was still a problem. No matter how mathematically perfect a telescope is, its images are distorted by the Earth's atmosphere, and some wavelengths cannot reach the ground. In 1946, astrophysicist Lyman Spitzer proposed a telescope in orbit above the Earth's atmosphere. The idea clearly outstripped the technology of the time. But by 1966, NASA began launching a series of orbiting astronomical observatories. Only 2 were successful, but the telescopes in low Earth orbit were the first to see the night skies in the ultraviolet part of the spectrum. In the 1970s, plans were drawn up for a large orbiting telescope. Part of its brief was for it to be visited regularly by maintenance crews, something that would become possible when the Space Shuttle went into service. The design called for a 2.4-meter primary mirror ground within very fine tolerances, because it was required to function well into the ultraviolet spectrum. Originally known as the Large Space Telescope, it was slated for launch in 1979, but delays in construction led to several postponements, and the Challenger disaster led to more delays. In 1983, the name Hubble Space Telescope was adopted in honor of the man who confirmed that the universe was expanding. Finally, in April 1990, Hubble was ready for launch.
Sound suppression water system has started. T-minus 13 seconds. T-minus 10, go for main engine start. We are go for main engine start, T-minus 6, 5, 4, 3, 2, 1, and liftoff of the Space Shuttle Discovery with the Hubble Space Telescope, our window on the universe.
Hubble has a unique relationship with the Space Shuttle, which would revisit the telescope on 5 different occasions. At this stage, nobody understood just how vital these missions would be. To deploy Hubble, the shuttle Discovery set a new altitude record of more than 600 kilometers. Release of the telescope was routine. It took several weeks methodically checking Hubble's control and communication systems before astronomers working at the Space Telescope Science Institute in Baltimore could see Hubble's first images. Results were disappointing. Images were blurred. The telescope's mirror had been accurately ground, but to the wrong shape. An incorrectly assembled test instrument had been relied upon during manufacture, and nobody had double-checked. Soon a fix was proposed. Because the error was understood, a corrective device could be fitted to the telescope. A series of small mirrors would compensate for the primary mirror's defect. It was called COSTAR, another of those cumbersome NASA acronyms. Training astronauts for the job of accurately installing COSTAR began. The high-speed photometer would be scrapped to make room for it. In addition to correcting the optics, a number of other modifications were set in train. A new wide-field planetary camera would be installed. The original was obsolete. The telescope's solar panels would be replaced. There would be a new electronics processor, extra magnetometers, and 2 gyroscopes would be replaced.
10, 9, and we have a go for main engine start. 5, 4, 3, 2, 1, and we have liftoff. Liftoff of the Space Shuttle Endeavour on an ambitious mission to service the Hubble Space Telescope.
Finally, in December 1993, the mission to repair Hubble began.
Roger, roll, Endeavour.
It took the Endeavour 3 days to catch up with Hubble, and it was clear from the beginning that one solar panel was damaged. The work on the telescope was considerable, and there were 5 spacewalks scheduled. Firstly, the shuttle's robotic arm grabbed the Hubble so it would remain stable while the work was carried out. The work would be shared between 2 teams of 2 astronauts. Over 5 days, the allocated tasks were carried out, with the Space Telescope Operations Control Center monitoring the Hubble's performance as each new component came online. Most of the parts replaced were stowed in the cargo bay for return to Earth, the one exception being the damaged solar panel, which was set adrift in space. All 5 spacewalks went according to plan, with the only major problem being the difficulty involved in closing the telescope's doors. On the 9th day of the mission, Hubble was released. It would take controllers on the ground another month to fully check the telescope's new systems. Hubble had been repaired in December 1993, yet it would take close to 2 months for technicians on the ground to run through a complex series of optical alignments before they could be certain that the telescope was performing correctly. When astronomers finally saw results, they were stunned at the quality it was delivering. The repair mission had been successful. With the services of a powerful new tool finally at their disposal, astronomers at the Space Telescope Science Institute began addressing a pressing list of demands for time on Hubble. In March 1993, a comet had been discovered orbiting Jupiter. Its path suggested that it had only recently been captured by Jupiter's gravitation and that it would soon crash into the planet. No one had ever seen a collision between bodies within the solar system, and opinions differed about how visible the impact would be. Soon, Hubble captured this image of a chain of fragments. Comet Shoemaker-Levy 9 had been shattered by Jupiter's gravitation. The fragments ranged in size from several hundred meters to several kilometers across. Over 6 days in July 1994, Hubble observed the pieces crash into Jupiter's unlit face. As the planet revolved, the impact region showed a series of black swirls. Some of the dark shadows were as large as the Earth, and they persisted in Jupiter's atmosphere for months. Spectral analysis from Hubble revealed diatomic sulfur and carbon disulfide. These had never been seen at Jupiter, yet the amounts detected were too great to have come in with the comet. They had been stirred up from the planet's interior. Scientists learnt so much from observing these impacts, yet the observations almost didn't happen. Just days before the first impact was due, Hubble began acting unpredictably and then went into safe mode. It would not execute any of its instructions. Technicians suspected a memory problem and took measures to switch across to new memory installed on the recent service mission. Things started to improve until the spacecraft reported it had entered zero gyro sum point. It appeared that 2 gyroscopes had failed and the situation had dramatically deteriorated. The problem was traced to a counter that had run out of numbers with which to count. The issue was understood and quickly resolved. The incident underlined just how complex the operations of the Hubble would be, and that the ground engineers still had to learn how to operate the new hardware. Though Hubble functions as a telescope, it is also a spacecraft that must be controlled with exquisite accuracy. Unlike other spacecraft, it has no thrusters. Chemical residue from rocket engines would quickly contaminate the precision optics. To enable it to move, Hubble has 4 reaction control wheels. As they spin, the telescope will rotate in the opposite direction. Each one has a mass of 45 kilograms, and they are controlled by the telescope's computer. Combinations of spin in any 3 wheels will allow the telescope to point accurately in any direction. They are mounted in angled pairs around Hubble's center of gravity. In 1997, on the Space Telescope's second servicing mission, one of the reaction control wheels was replaced. It had developed an electrical fault. So that Hubble can remain pointed accurately, 3 fine guidance sensors positioned toward the back of the telescope will lock onto any of a series of bright guide stars. Hubble only needs 2 guidance sensors to point with accuracy. They are so sensitive, they can detect wobble in the motion of closer stars. The third vital aspect of the telescope's pointing system is its ability to detect the rate and direction of its movement. Hubble is equipped with 6 gyroscopes that register its orientation. These are essential when pointing the telescope in a new direction. The gyros spin at 19,200 RPM and they do wear out. This is why there are 6 units, even though when designed, Hubble only needed 3 to function properly. With new algorithms, Hubble can now point with only 2 gyros, though less accurately. Work has been done to enable it to work at reduced capacity with only 1 gyroscope. Hubble can point with an accuracy better than 2/millionths of 1 degree. This ability to stay fixed on one narrow region of the sky for a very long time led astronomers to perform a unique observation. For 10 days in 1995, they pointed Hubble at a small, empty region of the sky near the constellation Ursa Major. To some, this was folly, a waste of valuable observation time. The results astounded everyone. This empty part of the sky was packed with irregular-shaped galaxies. Some were as old as 13 billion years. Hubble had looked back in time at the formation of new galaxies in a range of shapes not seen closer to our own Milky Way. It became known as the Deep Field Survey. It was the first of a series of similar explorations of areas of the sky in which nothing had previously been seen. Animators have added depth to these images by using spectral information known as redshift, which indicates a body's distance from Earth. This was a completely new area of astronomy, and it was one reason why Hubble had been built, but the Space Telescope was already running into design constraints. Engineers began work on equipment that would upgrade the telescope's performance in the near-infrared part of the spectrum. This would be fitted during the next servicing mission, along with updated support equipment such as a solid-state recorder, which would replace the original reel-to-reel recorder. Yet even at this early stage of Hubble's life, astronomers were realizing its limitations. The distant galaxies it had seen were approaching the extent of its view in the infrared end of the spectrum. Even with enhancements, the telescope could not be kept cold enough to observe the large redshift wavelengths, revealing very old, very distant objects. Plans were drawn up for a new, larger telescope, known as the Next Generation Space Telescope, that could explore the most distant parts of the universe. But there was still plenty that Hubble could do better than any other telescope, and there appeared no reason that it wouldn't continue being refitted with the latest technology as it became available. Early in 1997, the Space Shuttle Discovery visited Hubble for a second servicing mission. Astronauts fitted new instruments to improve its reach into the infrared. In 1999, Discovery again visited Hubble. This mission had been brought forward as 4 of the gyroscopes had failed and the telescope had gone into safe mode.
4, 3, 2, 1, and liftoff of Space Shuttle Columbia to broaden our view of the universe through the Hubble Space Telescope.
In 2002, Columbia lifted off with a new instrument, the Advanced Camera for Surveys. It would replace the Faint Object Camera, the last of Hubble's original instruments. When it departed, Hubble was again in peak condition. Less than a year later, at the close of its next mission, Columbia burnt up during re-entry. Foam insulation had come loose during launch, damaging thermal protection tiles. After an exhaustive search for debris and a thorough inquiry, it was decided that the shuttle system was aging. It would be retired upon completion of the International Space Station. All other missions were ruled out. For the Hubble Space Telescope, this was a death sentence. In the corridors of power, Hubble had friends. The sheer beauty of images from the telescope gave it a public profile, and key senators began campaigning for one last servicing mission. After a new administrator took charge at NASA, a final shuttle flight to Hubble was reinstated. Work began on what would amount to a rebuild of Hubble's operational systems, as well as another update of scientific instruments. New fine guidance sensors would be fitted. All gyroscopes would be replaced, and a new set of batteries would replace the originals that Hubble was still using. Within the imaging spectrograph, a power supply had failed, and training began to open up the unit and replace an electronics board. The Advanced Camera for Surveys had also malfunctioned, and its repair work was seen as even more detailed. Because the shuttle now had to operate with a backup, and because Atlantis could not reach the International Space Station from Hubble's orbit, the shuttle Endeavour was prepared for a rescue mission. On the 11th of May 2009, Atlantis sat on NASA's Pad 39A ready for Hubble's final servicing mission. This was to be the most complex servicing mission. It had to deliver the longest possible life for the orbiting telescope. The 14-day operation went according to plan. When problems arose, they were solved, and Hubble was eventually released as the best telescope it had ever been. On the ground, astronomers from the Space Telescope Science Institute waited for the first pictures from Hubble's new, more sensitive instruments. This means the telescope can operate more efficiently, needing less observing time than earlier incarnations. The team was quick to release examples of the new generation images. In the Eagle Nebula, the pillars of creation, thousands of light years from Earth, immense clouds of hydrogen and dust are giving birth to new stars. The 5 galaxies of Stephan's quintet in the Pegasus constellation. 4 of these are colliding. 16,000 light years from Earth, Omega Centauri in the constellation Centaurus is a globular cluster. Stars here are so densely packed that on average there is just 1/10 of a light year between them. While Hubble has been adding to its list of discoveries, everyone understands that without further servicing, the telescope will eventually die. That slow death has already started, and it's the gyroscopes that are failing. Engineers have been careful, operating just 3 gyros, keeping the other 3 as spares. By mid-2018, 3 of the units had ceased functioning. As the last of the 3 gyroscopes held in reserve was brought online, it misbehaved, and all science operations of the telescope were suspended. By recycling power to the unit, a measure akin to switching it off and back on, normal function resumed. As further gyros fail, the telescope will use its star trackers to help it point accurately. Hubble is expected to function well into the 2020s, by which time a new space telescope should be in orbit. The next generation space telescope is now called the James Webb Space Telescope, named after NASA's Apollo-era administrator. The telescope has been completed and is undergoing exhaustive checks before it is launched. It has a giant mirror of 18 hexagonal segments that is folded before deployment. Compared with Hubble, it is huge, yet the complete spacecraft weighs considerably less than Hubble. NASA built the Webb telescope in collaboration with the European and Canadian space agencies, and it will launch on an Ariane 5 from the European spaceport in Kourou, French Guiana. It will orbit at the second Sun-Earth Lagrangian point, a place 1.5 million kilometers from the night side of the Earth, where the telescope can maintain a stable position. A large, very thin sun shield will protect the James Webb, allowing the optical components of the telescope to cool to around 50 degrees Kelvin. Its operational temperature must be very low to allow it to see deep into the infrared end of the spectrum. The mid-infrared instrument needs to be colder still. A cooler using helium as its refrigerant will enable the sensor to function at just 7 degrees Kelvin. The Webb Space Telescope is designed to build on the work of Hubble by seeing further back to the earliest emergence of galaxies, stars, and exoplanets. From the moment a rocket lifts off, it is tracked and monitored. All vital performance characteristics are relayed back to the ground via telemetry. At huge distances, a probe must be able to communicate. On Earth, to pick up these signals, we use parabolic dishes. They range in size from small domestic units for television reception to the giants of the deep space network. Without these, almost any spaceflight would be pointless. The very first artificial satellite, Sputnik, was designed with 4 whip antennas and 2 radio transmitters. Soviet engineers saw its main function as announcing to the world that it was there. It transmitted a continuing series of beeps. Ham radio operators around the world could detect the signal. Very few realized that the beeps varied in duration according to the temperature and pressure within the sphere. The signals could also be analyzed for clues to the ionosphere's electron density. Soon, cosmonauts and astronauts were orbiting the planet. When John Glenn made the Mercury program's first orbital flight, 18 different tracking and communications posts were set up along his spacecraft's ground track. As well as local staff, NASA provided each ground station with its own capsule communicator, a flight engineer, and a flight surgeon. Special tracking ships were deployed to maintain communications and monitor telemetry while the spacecraft was crossing the ocean. But even so, the network had blind spots where the spacecraft was out of reach. For the Soviets, communication was even more difficult. During their early space flights, there were no tracking ships, and their terrestrial stations were all in the Soviet Union. When the Soviet Union launched Lunik 1 in 1959, it was intended to hit the moon. It missed and became the first craft to achieve solar orbit. Because it required special tracking infrastructure and was not monitored outside Russia, many in the United States refused to believe that the spacecraft had even been launched. At the time, the world's largest radio telescope was the Mark I installation at Jodrell Bank in the UK. Soon the Russians began sending detailed information about finding their probes to Jodrell Bank as a means of independently verifying their missions. In the early days of the space race, the Soviet Union had big plans for deep space missions. In 1959, construction work began on the Pluton facility in the Crimea. Though the Soviets did not enjoy the financial resources of the United States, they were not lacking in enterprise. The Pluton receiver consisted of 8 dish antennas welded onto pieces from the hulls of 2 war surplus submarines. They were mounted on a steerable frame made from the truss work of a railway bridge. To point the dishes with accuracy, the designer, Evgeny Gubenko, employed the mechanism from the gun turret of a scrapped battleship. The system worked well and remained in service till 1978. It had become clear to the space powers that communications support for low Earth orbiting satellites was very different to that needed for probes traveling into deep space. Deep space missions require much larger, more sensitive dishes with powerful transmission capabilities. Yet these probes' position in the sky changes more due to the Earth's rotation than it does because of the craft's speed. So while the dish has to point with great accuracy, it does not have to move very rapidly. Satellites in low Earth orbit pass close, so a smaller dish is adequate, but it must move rapidly to maintain a precise focus on its target craft. In the United States, corporations were taking an interest in a huge new type of satellite. Researchers were interested in using an orbiting balloon to relay radio signals across continents. Project Echo launched its first inflatable satellite in 1960.
This is President Eisenhower speaking.
A telephone call from President Eisenhower was relayed from Washington to California by bouncing signals off the balloon, which acted as nothing more than a reflector. In 1962, US phone company AT&T built Telstar. It was the first electronic relay satellite. Launched by NASA in July 1962, Telstar was the first commercially funded satellite. Europeans tuning in to see President Kennedy got baseball and then the presidential press conference.
I understand that part of today's press conference is being relayed by the Telstar communications satellite.
Then French singer Yves Montand sang a song to the US.
Faire son métier, le public se souvient. La chansonnette, tiens, tiens.
As far as it went, it was a success. But Telstar's low orbit meant it was only available for 20 minutes every 2.5 hours, and Telstar's life was cut short as a result of the Cold War. Both the Soviet Union and the United States had been detonating thermonuclear weapons above the atmosphere to determine whether this was a viable anti-missile strategy. From tests in the Pacific, they discovered that an immense pulse of gamma radiation triggered positive ions and recoil electrons that took out electrical systems in Hawaii and New Zealand, destroyed at least 3 satellites, and damaged several others, among them Telstar. In October 1963, US President John Kennedy added his signature to a treaty with the Soviet Union banning nuclear testing in space. The first telecommunications satellite that resembled today's technology was Intelsat-1, also known as Early Bird. It orbited above the equator at the same rate as the Earth's spin, which allowed it to hold a static position. It could relay 1 TV channel or 240 telephone calls. It was the beginning of the space business's most profitable industry. Estimates put satellite telecommunications revenues for 2019 at $2.4 trillion US. Geosynchronous orbits make ground stations much simpler without the need to track a target across the sky. Today, there are at least 240 active satellites in equatorial orbit at geosynchronous altitudes. Not all are communications platforms. Weather satellites also find this orbit useful, having an uninterrupted view of a complete hemisphere. The craft must be carefully spaced to avoid collisions and radio frequency interference. The International Telecommunications Union coordinates the orbital slots and frequency allocations, and satellites nearing the end of their useful life must retain enough fuel to boost themselves into a graveyard orbit to prevent overcrowding. There is clutter caused by spent upper stages and old satellites. Another highly specialized group of communication satellites is also stationed in geosynchronous orbit. NASA currently operates 10 tracking and data relay satellites, TDRS. Originally designed to provide a continuous communications link for shuttle missions, TDRS supports many near-Earth satellites, as well as the International Space Station, the Hubble Space Telescope, and some military applications. Similarly, ESA has launched 2 of what will be a group of 4 data relay platforms to provide a continuous link with near-Earth satellites. Instead of transmitting to ground stations, only visible for brief parts of every orbit, many satellites now send signals up to a data relay spacecraft that can see it for half of each orbit. A network of relay satellites around the globe gives continuous coverage. All major space agencies have been experimenting with data transmissions via lasers, but the EDRS system is the first commercial application of optical communications between spacecraft. Current laser communications techniques between satellites deliver data at 1.8 gigabits per second, 30 times greater than conventional radio links. However, weather-related problems inhibit reliable laser connections between spacecraft and Earth. Transmission back to the ground is via microwave radio in the Ka band. While this is fast, it is still slower than the laser data rates, but the signal can be split into several streams and sent simultaneously. Europe's Copernicus system is a major beneficiary of the near real-time data available via the EDRS system. Copernicus is an Earth observation program relying on a series of Sentinel satellites that send back continuous streams of data about the land, the oceans, and the atmosphere. The Copernicus program is not a limited project. It is designed to collect authoritative data about planetary changes over the long term. To do this, the Sentinel satellites are in low north-south orbits, allowing them to see the Earth's entire surface every 24 hours. This polar orbit is common to every Earth-observing satellite. But not every satellite has access to the EDRS communication system, nor do they generate the vast amounts of high-resolution data that requires it. Most satellites following a polar track rely on the polar receiving installations that they pass above every orbit. On the Norwegian archipelago of Svalbard, the Svalsat installation has 31 radomes to track and download data from satellites in polar orbit. To relay the information to the outside world, twin fiber optic cables, each handling 10 gigabits per second, connect Svalbard to the Norwegian mainland. Koenigsberg, the company that operates the facility for the Norwegian government, runs a smaller station in Antarctica. There are close to 1,900 operational satellites in Earth orbit, with a further 3,000 still orbiting as space junk. But there are as many as 20,000 fragments from spent boosters and debris from collisions that must be tracked. Operational satellites are routinely moved when an object approaches on a dangerous course. If this picture appears crowded, it is about to become a lot more complex. The US Federal Communications Commission recently gave rocket company SpaceX approval to launch 12,000 new satellites for its Starlink broadband internet service. Current satellite internet services rely upon a very few large platforms in geosynchronous orbit. Typical users are in remote locations, and while costs are coming down and speeds are improving, latency or response time is sluggish. The Starlink model has thousands of small satellites in low Earth orbit, cross-linked via high-speed lasers. The satellites will be able to adjust their orbital path autonomously to avoid collisions. The company launched its first batch of test satellites in May 2019. The second group, launched in November 2019, consisted of 60 operational satellites. For one company to increase the number of functioning spacecraft by a factor of 6, cost is critical. The satellites are being mass-produced in a flat pack form with a single solar panel. 60 will stack neatly within the fairing of a Falcon 9 launch vehicle. The Starlink satellite design is pushing the latest technology to its limits. Links to the ground are via a phased array, enabling a steerable beam without the need for moving parts. Maneuverability comes from a Hall effect thruster using krypton as its propellant. When released from the booster, the satellites do not require dispensing hardware. They are pushed away by springs in apparently haphazard fashion. At this stage, they can even bump each other and are designed to withstand the impact.
This is the highest number of satellites.
Quickly, the satellites orientate themselves and begin spreading along their orbital path. At this point, they can be seen in the pre-dawn or just after sunset. research astronomers are not happy about the huge number of satellites soon to be in orbit. By 2024, there should be 11,927 Starlink satellites orbiting at 7 different heights. The only satellite constellation remotely similar is the Iridium NEXT system, with 66 satellites cross-linked via the Ka band. They're designed to provide global cell phone coverage, and in 2018, the Iridium company finished the replacement of all its first-generation spacecraft. The upgrade cost Iridium $3 billion. For 200 times more satellites, SpaceX has budgeted $10 billion. Iridium had to pay Thales Alenia to design and build 81 satellites. There are spares both in orbit and on the ground. And it had to pay SpaceX to launch those satellites in batches of 10. With Starlink, the company will take advantage of its own drive to reduce expensive launch services. SpaceX builds its own satellites and its own rockets, so it will only pay cost for hardware and delivery. Recovery of first-stage boosters is now routine, which takes a large chunk out of launch costs. And the protective fairings, always regarded as throwaway items, are now fitted with steerable parachutes for retrieval and reuse, saving a further $5 million per flight. What will give Starlink its edge is its improved latency. In most cases, the system should give even better latency figures than fiber optic connections on the ground, let alone the half-second delay built into systems that send signals 35,000 kilometers up to and back from geosynchronous platforms. For stock markets reliant on high-frequency trading, microseconds make a significant difference. SpaceX believes people around the world will want the service. OneWeb and Amazon's Project Kuiper have announced plans to develop their own low Earth orbiting broadband systems. But with just the smallest fraction of the Starlink constellation in orbit, astronomers are starting to worry. Survey telescopes that use time exposures to map the skies, looking for anomalies like approaching asteroids or exploding stars, have recorded dusk and dawn images marred by Starlink satellites. Researchers from the Large Synoptic Survey Telescope, currently under construction in the Chilean Andes, have run simulations suggesting that as the Starlink constellation takes shape, certain observation times will be unproductive. Yet the Starlink venture itself is still a risk. Satellite businesses like Teledesic and Skybridge, both with big plans, went under. And SpaceX leader Elon Musk admits that success with Starlink is far from a sure thing. Communications with very distant exploratory spacecraft are governed by different parameters. The New Horizons probe, launched in 2006, is equipped with the most advanced digital technology ever to reach deep space. While its primary target was the dwarf planet Pluto, it passed Jupiter in 2007 for a gravitational boost to its speed. At Jupiter, a mere 2.3 billion kilometers from Earth, it transmitted images at 38 kilobits per second. That's slightly slower than an old acoustic telephone modem. At these distances, signal strength from New Horizons was weak, and only the 35 and 70-meter dishes in NASA's Deep Space Network were useful receivers. Even so, the data rate was slowed to deliver a coherent signal. Sending commands to the spacecraft is an exacting process. All instruction code is thoroughly reviewed by different teams before being tested on a simulator. Only then are they sent to the spacecraft. Because the environment around Pluto was so poorly understood, controllers on the ground relied on preliminary images returned by the spacecraft to make a hazard search. Distant encounter observations commenced 7 months before its close pass. As New Horizons approached Pluto in 2015, it had at least 16 different science objectives, along with spacecraft control and data management procedures, all pre-programmed. There could be no last-minute corrections. The spacecraft was traveling at more than 49,000 kilometers per hour, and signals from Earth took close to 4.5 hours to reach the New Horizons probe. During the critical close approach, there was a 22-hour radio silence because the spacecraft could only make its scheduled observations with its high-gain antenna angled away from the Earth. Everything was committed to the 8 gigabytes of storage in the primary data recorder. To retrieve that data took 16 months. At a distance of 4.7 billion kilometers, the New Horizon data rates were down to 2 kilobits per second. Only the 70-meter dishes in NASA's Deep Space Network could detect the signal, and they could not work exclusively with New Horizons. New Horizons kept going into the icy debris field known as the Kuiper Belt. Even as it was still transmitting data from its Pluto encounter, engineers on the ground formulated a series of course adjustments that would take it past object MU-69. The first time a probe was targeted at a body unknown when the craft was launched. In January 2019, New Horizons encountered the Kuiper Belt object Arakoth, formerly known as Ultima Thule. At a distance of 6.6 billion kilometers, data from the spacecraft took 6 hours and 7 minutes to reach Earth, and the data rate had dropped to 500 bits per second. It's still trickling in. Finally, the most distant probe is Voyager 1. It was launched in 1977 and is now outside the solar system at a distance of 22 billion kilometers. The probe transmits data as it is registered, and the Deep Space Network tries to gather at least 16 hours per day of the data stream that comes in at 160 bits per minute. This is roughly equivalent to a telegrapher sending Morse code.